Alright guys, it's time to put it all together. We're going to use everything we know to draw the graph of a function. Before we start, I want to point out that this is just one example on this video. There are many, many more examples in the book, and I suggest you read them. We'll also do some in class, but as you'll see, each example takes some time, so we won't be able to do very many in class, maybe only one, possibly two. And so I really highly encourage you to read the examples in the book. However, the book does have a section about slant asymptotes. We're not going to deal with those. You don't need to worry about it. Read it if you're interested, but it won't come up in the homework or exams. Okay, when we want to sketch the graph of a function, we're given the formula for a function, we want to sketch a graph. The first thing to do is figure out the domain, that is, which x values actually appear in the graph of the function. We want to see if we expect the graph to have any symmetry or be periodic. Symmetry like mirror image symmetry over the y-axis or rotational symmetry, those are even and odd functions. Periodic functions generally will be related to trig functions, which repeat themselves every 2 pi or every pi. We'll look for asymptotes, both vertical and horizontal. We'll take the first and second derivatives of the function and use all the information that gives us. Remember, we know that first derivatives can tell us about increasing and decreasing intervals and local maxes and mins. Second derivatives can tell us where the function is concave up or concave down and where there's inflection points. So all that information comes from derivatives. We'll actually find some points on the graph. In particular, we'll plug in the x values of any important points we've found to find the y coordinates. And then we'll have some points to plot. And finally, we'll connect all that information together with curves, thus drawing the graph. So this is going to be one example, and the example is the function 2x squared over x squared minus 1. The domain of this function. What x values make this function defined? Well, it works as long as the denominator is not 0. So all x except x equals plus or minus 1. That means the domain consists of 3 intervals, negative infinity to negative 1, negative 1 to 1, and 1 to infinity. So I expect my graph will have something drawn at every x value except nothing at x equals negative 1 and nothing at x equals positive 1. Okay. To check for symmetry, what we do is plug in negative x into the function instead of x. In this case, that simplifies and gives us 2x squared over x squared minus 1. That's exactly the same as the original function. If you get exactly the same as the original function, that means you have an even function, and thus it has mirror image symmetry across the y-axis. So the left half of the graph should be the mirror image of the right half of the graph. In theory, that means I might only need to deal with things bigger than 0, x values bigger than 0, because then I could just do the mirror image. But I think it's just as easy to do everything, so I'll just go ahead and do the whole graph. But we should expect it to be symmetric across the y-axis when we're done. If, when you plug in negative x, instead of getting the original function back, you get the negative of the original function, right? Every term becomes negative, then that's called an odd function. And that has 180-degree rotational symmetry around the origin, so it would look something like this. Notice if you spin that 180 degrees around the origin, it looks roughly the same, whereas the kind of symmetry we're going to have is mirror image symmetry, where if you folded it, it would match up instead of spinning it. If, when you plug in negative x to your function, you don't get the original and you also don't get the opposite of the original function, then your function doesn't have any kind of symmetry, and so that's all you know. Okay, I'm not even going to check for periodicity because there's no trig functions. It's not going to be a repeating periodic function. Okay, still same example function. Now we look for asymptotes. Two kinds, horizontal asymptotes and vertical asymptotes. Horizontal asymptotes we dealt with in the last section. Horizontal asymptotes have to do with what happens when you take the limit of your function as x approaches infinity. We do some calculations, and in this case we get 2. So that means that there is a horizontal asymptote, y equals 2. And since that happens as x approaches infinity, that's where the graph will level off towards the right of the function. We also need to check for what happens as x approaches negative infinity, but the same calculations here will work out. Again, because it's symmetric, whatever happens on the right will happen on the left. So y equals 2 is the horizontal asymptote on the left as well. Both ends of the graph will sort of level off at y equals 2. So we just have one horizontal asymptote. Okay, vertical asymptotes. Those generally happen when you have a denominator equal to 0. Remember, vertical asymptotes are when a limit as x approaches some number is infinity or negative infinity, so the graph shoots up or down. That happens when the denominator is 0, but not every time the denominator is 0. So you need to find the places where the denominator is 0 and then check them. In our case, the denominator is 0 at 1 and negative 1. So we have 4 one-sided limits to compute. X approaches negative 1 from the right, x approaches negative 1 from the left, x approaches 1 from the right, and x approaches 1 from the left. For each of these guys, we'll take a limit, and if you put in a number close to negative 1 but a little bit to the right, that is like negative 0.999, you realize that the function is around 2 on top and slightly less than 0 on the bottom, so you get negative giant numbers. So that limit is negative infinity. This is stuff we did back in chapter 1. If we do the same sort of analysis for the other 4 limits, we get some infinities and some negative infinities. Well, what does that mean for our graph? Well, it means there are, in fact, vertical asymptotes at both x equals negative 1 and at x equals 1. And in fact, we know sort of what happens at those vertical asymptotes. So at x equals negative 1, from the left, the limit was infinity, so it goes up from the left. From the right, the limit was negative infinity, so it goes down from the right. And the asymptote at x equals 1 has sort of the opposite shape. From the left, it goes down, and from the right, it goes up. So now we know the asymptotes. We have a horizontal asymptote at y equals 2, and these 2 vertical asymptotes. Moving on. Derivatives and all the information that the derivatives will give us. So we take the derivative. I have to use the quotient rule, and I can simplify a bit. And I get negative 4x over x squared minus 1 squared. Okay, so that's the first derivative, f prime of x. What am I supposed to do? Well, I'm looking for where the function is increasing, decreasing, and local maxes and mins. So I need to find all the places where f prime is 0. That's just at x equals 0, because if the fraction negative 4x over x squared minus 1 squared is equal to 0, that means the numerator is equal to 0. I also look for places where f prime doesn't exist. That's when the denominator is 0. And that happens when x is plus or minus 1. That's not surprising because the function didn't exist when x is plus or minus 1, so its derivative won't exist there either. And then remember, we do this number line thing. At least this is the way I do it. So I draw a number line for f prime, and I put these important x values, these critical numbers on it, 0, 1, and negative 1. And then in each interval, I figure out whether f prime is positive or negative. Now in this first interval, x is negative, which means negative 4 times x is positive. Since my f prime is negative 4x over a square, and squares are always going to be positive, that means I've got negative 4x over a square. That's a positive number over a positive number, so f prime is positive in this interval. So I put a plus sign. Okay, in the next interval, x is still negative, so negative 4x is still positive, so f prime is positive, and I put a plus sign. In this interval, x is now positive, which makes the numerator negative 4x negative, and that makes the whole f prime negative, because the denominator is still a perfect square, it's still positive, so I get a negative sign there, and the same thing here. Positive x makes f prime negative. So there's my information about f prime on the various intervals. Positive, then negative, then negative. What does that mean? Well, it tells me f is increasing on these first two intervals, from negative infinity to negative 1, and also from negative 1 to 0. Something weird might happen at negative 1. In fact, we know something weird happens. It's a vertical asymptote. It's decreasing on the minus intervals, from 0 to 1 and 1 to infinity. Again, weird vertical asymptote at x equals 1. This also tells me there's a local maximum when we switch from increasing to decreasing. That happens at x equals 0. So there's a local maximum, and I don't see any local minima. There's no place where it switches from decreasing to increasing. Okay. So that's what we got out of the first derivative. Now we need the second derivative. So I have to take the derivative of the derivative. Again, quotient rule, yay, lots of fun. And I'm not going to show you the steps for simplifying here. Trust me. Okay. Here's the second derivative. 12x squared plus 4 over x squared minus 1 cubed. That's as simple as it gets. Okay, so again, I need to look for the places where that, the second derivative, is 0 or doesn't exist. F double prime equals 0, I would need to solve 12x squared plus 4 equals 0, and that would mean x squared would have to be a negative number, so that's not going to happen. There's no solutions for that. The does not exist part happens when x minus 1 cubed equals 0, and again, that's when x equals plus or minus 1. So our number line for f double prime just has 2 points on it, 1 and negative 1. Again, we're going to look at each interval and decide whether f double prime is positive or negative. And notice in this situation, the numerator, 12x squared plus 4, is always positive. It's a perfect square times a positive number plus a positive number. Everything stays positive. So the numerator is always positive, so I really only have to worry about the denominator being positive or negative. Okay. X squared minus 1. If x is to the left of negative 1, x squared is bigger than 1, so x squared minus 1 is positive. So that means f double prime is going to be positive, and I put a plus. In this middle section, x squared is smaller than 1, so x squared minus 1 is negative. So when you cube it, it's still negative. That makes the denominator negative. Positive numerator, negative denominator makes the whole thing negative, and I get a minus sign. And same sort of idea, I get a plus sign in the third interval here. If x is bigger than 1, then this f double prime of x will be positive. So that tells me f is concave up on the outer two intervals and concave down in that middle interval from negative 1 to 1. And now I look for inflection points. Inflection points, remember, when the graph switches concavity from concave up to concave down or vice versa. So when f double prime switches from positive to negative or vice versa. So you might think there would be inflection points at 1 and negative 1. But they're not, because inflection points have to be points on the graph. And when x is 1 or negative 1, the function doesn't even exist. So there's not a point on the graph when x is 1 or negative 1. So although the concavity switches at that x value, it doesn't switch at that point on the graph because there's no point on the graph. So this graph doesn't actually have any inflection points, even though it switches from concave up to concave down, back to concave up. All right. Finally, well, not finally, points. Okay. This just means each important x value that we've found, we're going to plug it into the original function f of x to get some y values, so we know some points to plot on our graph. And if x equals 0 isn't one of our important points, we'll plug that in too. That'll give us a y-intercept. Now, what do I mean by important points? I mean local max x values, local min x values, inflection point x values, any of the critical numbers, those kinds of things. In this case, x equals 0 was one of those, right? It was a local maximum at x equals 0. So we're going to plug that into the function. You get 2 times 0 squared over 0 squared minus 1. That's 0. So the point 0, 0 is on the graph, but this example is boring because, well, the point 0, 0 is kind of boring anyway, but also that's the only important x value I have. There were no other local maxes or local mins. There were no inflection points. I plugged in x equals 0. It was an important point, but it also gave me the y-intercept, which is y equals 0. And that's it. So I only have one point to graph. That's x equals 0, y equals 0. So now I get to start trying to draw my graph. And this is going to get a little chaotic with the drawing, but I hope you can sort of follow what I'm doing. So here's my axes, and I'm putting a few hash marks, 1, 2, 3 to the right, 3 up, 3 to the left, and a couple down. And the first thing I draw in there is the horizontal asymptote I found, y equals 2. Okay, so the graph should approach that horizontal asymptote out to the edges. I also have two vertical asymptotes at x equals 1 and x equals -1. And I know which direction we approach those vertical asymptotes from. Right? When I found the asymptotes with the limits, I got this information. So there's parts of the graph I know. I also know that point from the last step. At 0, 0, my graph should hit, so I have to go through that point, 0, 0, the origin. And now, everybody has different ways they like to draw this stuff, but here's some information about increasing and decreasing, right? My function should increase all the way up to that vertical asymptote, then it increases a little more, then it decreases all the way from that vertical asymptote to forever. I also have concave up in that first section, and in the outer last section, and concave down in the middle. So now I need to connect the points and pieces of curves I've got with curves that satisfy all these requirements, and also mirror image symmetry left to right. Well, there's a part of the graph that is increasing and concave up in that first section, decreasing and concave up in the right-hand section there, and both of those level off at that horizontal asymptote. They should look like mirror images of each other. I'm not that good at drawing, so they don't exactly, but you get the idea. And then in this middle strip, I need to go through that origin, go down on both edges. It needs to be concave down, increasing and then decreasing, and hit a local max there at the origin. And so that's roughly what I get, a sort of tall, skinny, upside down shape that has a local maximum at the origin. Okay, so that the black curves are the graph of my function. The blue dotted lines are useful to draw as well, the horizontal asymptotes. You don't need all that other stuff written there, but I use it to help me draw the graph, so you can either draw it when you're doing it and then erase it at the end or leave it there. That's fine. But the graph and the asymptotes are what you need to have. All right. We will do more of these in class, but again, I highly, highly, highly recommend that you read some more examples in the book in section 3.5. I'll see you in class.